now Teresa Terolli will tell us about more about locality-sensitive hashing.
Okay, so good afternoon, everybody. I'm Marisa. Today I'm going to present our paper entitled "The Distortion of Locality-Sensitive Hashing." This is a joint work with Flavio Chiarichetti and Alessandro Panconesi from Sapienza University of Rome and Ravi Kumar from Google Mountain View. So in data analysis, computing the similarity between two data objects is one of the basic problems. There exist many different types of similarities out there in literature. On one hand, we have set similarities. For instance, Jacquard, which is the intersection over the union, Brown-Blanquet, Hamming similarity. On the other hand, we have vector similarities, for instance, the famous cosine similarity. However, a very fundamental problem, given a specific similarity S, is to compute it efficiently. Locality-sensitive hashing is an efficient way to compute similarity between two data objects. Locality-sensitive hashing was initially introduced by Broder in 1997 when he introduced shingles to estimate the Jacquard similarity between two different documents given as a bag of words. There exist two different definitions of locality-sensitive hashing. In this presentation and for the rest of the paper, we are going to use the definition proposed by Chiarichetti in 2002. A locality-sensitive hashing, or short LSH for a specific similarity S, is a probability distribution D over a set of hash functions such that for every pair of object x and y defined on the universe, we have the probability that the hash function of x is equal to the hash function of y is exactly the similarity between x and y. Let's illustrate this definition by a toy example. Suppose that we want to compute the similarity between object x and object y. And then you pick at random k hash functions according to the probability distribution D. Now, for each of the hash functions that we pick, we compare the hash function value of x to the hash function value of y. And then we conclude by the law of large numbers that the similarity between x and y is approximately the number of collision, meaning the number of times that h of x matches h of y over the total number of hash functions picked, which in this case, it's k. It's well known that locality-sensitive hashing is extremely useful in theory and in practice. For instance, in 2012, Broder, Chiarichetti, and Indyk received the ACM Paris Kanellakis Award for their work on locality-sensitive hashing. It's cool when a similarity has such a scheme. However, there exists a wide range of similarities who do not have an LSH. A natural question is, what can we do with this set of similarities that do not admit such a scheme? So the main problem that we want to tackle in this paper is as follows. Suppose that you have a similarity which do not have an LSH. In other words, it's not LSHable. Are we able to find another similarity S prime which is LSHable and can help us approximate our initial similarity S? To answer this question, in this paper we introduce the notion of distortion. But what do we mean by distortion? So let's have a specific similarity S, which it's not LSHable. And suppose that there exists another similarity S prime, which is LSHable. And also suppose that the value of S prime is sandwiched between S over delta and S for every pair of x and y defined on the universe. We define the distortion of similarity S as the smallest value of delta. Note here that if delta is equal to 1, then S itself is LSHable. And if the universe is infinite, then smallest becomes infimum. Then we explore the notion of distortion and we prove sharp upper and lower bounds for a wide range of similarities. Some examples of well-known and widely used similarities are listed in this table with their lower and upper bounds on the distortion. Note here that all the bounds are tight except for Sokol-Smith gamma infinite family of similarities, which might be a really interesting research problem for future research. Now, computing upper bounds on the distortion is simple. It can be done using existing techniques like shingles or rational set similarities. Which is more technically involving are computing lower bounds. For the rest of the talk, I'm going to talk about techniques on determining the lower bounds on the distortion for a wide range of similarities. So by Charikar in 2002, we know that if a specific similarity admits an LSH, then the following two conditions are true. 1 minus S is symmetric, and also 1 minus S is isometrically embeddable into L1. So these two conditions are two necessary conditions for LSHability. However, we can ask, are these two conditions sufficient? And the answer is no, they are not. Why? Because in this paper we prove that Brown-Blanquet, which is defined as the intersection of two sets over the cardinality of the bigger set, is isometrically embeddable into L1, which means that it passes both T1 and T2 tests. However, its distortion is equal to 2. Remember here that a similarity is LSHable when its distortion is equal to 1. So we can conclude that Brown-Blanquet is not LSHable. Now, in order to determine our lower bounds on the distortion, we have, let's say, introduced two technical tools. We named the first one the center method, which is a really simple and useful averaging argument. And the second one, we called it the K-set method, a method that works for similarities over sets. The second method is too involved for this short presentation, and I really encourage you to refer to our paper for more details. Now I'm going to give the main idea behind the first method, named the center method. So let's have similarity S to be an LSHable similarity. We know that by Charikar that the distance D, which is 1 minus S, is symmetric. And then suppose that the set of points A is the set of points that are totally dissimilar with one another. And by totally dissimilar, I mean having a maximum pairwise distance. In other words, the distance between X and Y is equal to 1 for all the pairs X and Y defined on A. Then, if we pick any other point Z, which is not in the set A, then we will always find a specific point X in A, which is almost totally dissimilar with our point Z. In other words, the distance between X and Z is greater or equal to 1 minus 1 over the cardinality of the initial set A. So this is a really strong property induced by LSH spaces, and we can exploit this property to prove lower bounds for a wide range of similarities. Please note here that neither metric spaces nor L1 spaces have this property. We can use the center method to define the distortion on an infinite family of similarities named as Sorensen gamma, which is defined as the intersection over the intersection plus gamma times the symmetric difference. As you can see from the plot, if gamma is greater than 1, then all the similarities are LSHable, meaning that their distortion is 1. And for gamma smaller than 1, the distortion is 1 over gamma. Some special cases of Sorensen gamma are the famous similarity like Sorensen Dice, Jacquard, and Anderberg. So to conclude with, we have introduced the notion of distortion as a worst case notion because we pick the worst pair of data object in our data set. It's really important to know what happens using real world data sets. To answer this question, we have conducted a series of experiments using public available data sets, exactly Archive, CiteSeerX, and Wikipedia, and we wanted to approximate Brown-Blanquet, whose worst case bound is equal to 2, by shingles of Jacquard. And then the procedure of the experiment is very simple. For each of the data sets, we have picked 50 million pairs of documents, and we have computed the distortion given by Jacquard of Brown-Blanquet. On the x-axis of the plot, you can see the value of distortion, and in the y-axis, you see the percentage of pair of documents that have this specific distortion. As you can see from the plot, the average distortion using real data sets is smaller compared to the worst case bound, which gives us some hope that maybe things are better in average. To conclude with, in this paper, we have introduced the notion of locality sensitive distortion for similarities who do not admit an LSH. We also obtain sharp upper and lower bounds for a wide range of similarities. By conducting experiments, we show that in average, the distortion is smaller compared to the worst case. And we leave as an open problem the question of determining the right notion of average distortion. Thank you. Any question?